Hello, Math Humans. We're going to do 4.2 today. We're going to be doing area by summation as my paper runs away. Our objectives are that we're going to approximate the area, the two-dimensional area, three-dimensionals coming soon, woohoo, under a curve using sigma notation. So if you'll go back and remember when we started derivatives, we would apply a limit to a derivative. And we were talking about as, if I'm trying to calculate, remember that we did a tangent line approximation and we're looking for our x1 and our x2. We were looking for the limit as delta x goes to 0. We're going to apply the same type of concept to the area under a curve, except we're going to take a slightly different approach. But we are going to be taking a limit. Alrighty. So if we go back and remember sigma notation, okay, we learned and talked about sigma notation in pre-calc. So this is my epsilon, means sum, and I'm going to sum from the first term to the nth term, and then this is my rule to generate the terms. And so it would be a sub 1 plus a sub 2 plus a sub 3 all the way up to a sub n. I is called the index of summation. A sub I is the individual term. I equals 1 says start here, that's your lower boundary, and n is going to be where we stop summing, and that's going to be my upper boundary. If you will remember, if I go to my math button, okay, and then I scroll down, my summation is right here. So, oops, as I push the wrong buttons, there is my summation. So I can do summation notation in my calculator, but we are going to be doing these problems by hand. But there is an application that you can use on your calculators. Alrighty. So the next thing that I've pre-written for us are the summation formulas. And here are the summation formulas. And I think I neglected one as I was trying to push us along for time. So if I have I is equal to 1 to n of a constant times a sub I can take the constant out front, and then I could have my a sub I, okay? These are formulas that are already on your formula sheet, and we will be using these formulas as we progress through these problems. Alrighty. If I do our first example, since my paper doesn't seem to want to behave, I'm going to do the sum I equals 1 to n of I plus 1 over n squared. So in these types of problems, until you manage the I, n is going to be treated as a constant. Okay, and then once we manage the I, then we're going to use our material. So I'm going to pull this out front since it's a constant. So I'm going to write this as 1 over n squared times the sum from I equals 1 to n, and then I have I plus 1. And that's going to simplify our problem. Okay. Now I'm going to use my summation formulas. Okay. So I'm going to rewrite this again. So it's going to be 1 over n squared. And then my I, so I'm going to put a big parentheses, is going to be n times n plus 1 over 2, and then if I have a constant, then it's going to go up, okay? Just like with integration, it's going to go up in power. And so then what I'm going to do is I'm going to expand and clean up the inside a little bit. So I'm going to leave my 1 over n squared, and I'm going to have n squared plus n over 2. And just for purposes of math, I'm going to go ahead and put this together. I multiplied by 2 over 2, okay? So now if I clean that up, I'm going to have 1 over n squared times n squared plus 3n over 2, okay? So now what I'm going to do is I'm going to go ahead and distribute this into the problem. So I'm going to get n squared over n squared, and then I'm going to get 2n squared, and that would be this one right here. And then I'm going to do 3n over 2n squared. Notice those cancel, and my thing went away. There, now it's back. and it leaves me a half, and then I'm going to have an n down here in the bottom, so I have 3 over 2n, okay? And I could, if I chose to, I could simplify this more, and I'm just looking at my math. I think I did okay. Alrighty. I could leave it like this, or I could put it back together, but I'm just going to write that the sum from I equals 1 to n of I plus 1 over n squared is going to equal a half plus 3 over 2n. Okay, and that's where I would stop. So now what I want to do is I want to talk about a little bit of theory. Okay, so let's say I have a curve, and here is my curve. Notice that it is an increasing function, okay? So I can calculate the area under the curve by doing a series. Boy, my rectangles are looking pretty sad. Maybe if I go this way, it'll be better. There we go. Whew. I can estimate the area under the curve by drawing a series of rectangles, okay? So the area would equal the integral from a to b of whatever my function was dx. That's going to be the fundamental theorem of calculus, okay? But right now, instead of doing it this way, I'm going to sum the individual rectangles, okay? So, and you can't see that, so let me move it up a little bit. So I'm going to sum the individual rectangles. So maybe I have rectangle 1, rectangle 2, rectangle 3, and rectangle 4. So the area would equal the sum from I equals 1 to 4, and then I would sum my rectangles, okay? And I'm going to just write it like this instead of using a formula, okay? So then I could figure out the area of each rectangle. Area, remember, for a rectangle is going to be the base times the height, okay? All right, so in these types of problems, the height of the rectangle is going to be determined from the function evaluated at a point, and the base is going to be delta x. And so this is going to be how I would calculate the area of each individual rectangle. There's my multiply. And then the area from A to B is going to be the sum of these individual rectangles. Okay? Sometimes, and I'm going to just do it up here, if I have a curve, maybe I have a decreasing curve, and my rectangles are underneath, okay? So sometimes my approximation can be an over approximation, and sometimes my area approximation can be an under approximation. Alrighty. So as we continue along this conversation, we're going to get some formulas, and I'm just going to start writing things down for you. So the area of a rectangle is going to equal the base times the height, okay? So the base, we've already talked about this, is delta x. The height is going to be the function evaluated at some x values. X sub I is going to equal a plus delta x times I, or it can be x sub I is equal to b minus delta x times I, okay? This is going to be called a left-hand approximation, and this one is going to be called a right-hand. And if you'll think about when I had my intervals, so here was my curve, and we're trying to calculate the area from A to B, it's going to either be A plus, which is left, or B minus, which is right. My delta x is going to be b minus a divided by n, okay? And that's going to be if all of my rectangles are the same size. And then n is going to be the number of rectangles. Okay, So those are going to be the variables as we process through. And then my area is going to equal the sum from I equals 1 to n of f of x sub I times delta x. Okay? Alrighty. So I want to explain the theory behind this a little bit more. Okay? So let's say here is my curve, and I'm trying to calculate the area from A to B. I could calculate that by doing one big shape, and to me this looks like a trapezoid. So I could calculate the area under the curve by using a trapezoid. Or I could, same situation, draw a series of rectangles. And maybe in this case I have 3 rectangles, and I could approximate the area. Well, what happens if I divide the number of rectangles in half? Right? Well, then my approximation is probably going to be more accurate. Well, what happens if I divide it in half again? And now my approximation is going to be even more accurate. So just as we did derivatives with a limit, eventually what's going to happen is we're going to do the limit as n goes to infinity, meaning the number of rectangles goes to infinity, of the sum from I equals 1 to n of f of x sub I times delta x. And basically what we're doing, as the number of rectangles increases, then that's going to give me a very accurate representation of the area under the curve. And I would write this as the area under the curve. And ultimately, that's going to be the integral from a to b of f of x dx. So that's the theory behind what we're going to try to do. Okay? All right. So let's start with another example. I guess this is example 2, so we're not starting. We're continuing. And I want to find the area under the curve for y equals x squared, and I want to do it from 0 to 2, okay? So we're going to have n sub-intervals, okay? Alrighty. And on this one, I'm going to do a left-hand approximation, so this is really important. So I'm going to do the limit as n goes to infinity of the sum from I equals 1 to n of f of x sub I times delta x. So when we do these problems, it's really important that you are very consistent in the method that you use. So the first thing that I do is I calculate delta x. And delta x is b minus a divided by n. So it's going to be 2 minus 0 divided by n. So I'm going to write that as 2 over n. The next thing that I'm going to do is I'm going to figure out x sub I. And we're doing a left, so I'm going to write a plus delta x times I. Okay, so it's going to be a, which was 0, and then plus my 2 over n, there's my delta x times I. Okay, the next thing that I'm going to do is I'm going to do f of x sub I. So I'm going to substitute the 2i over n into my original function. And so I'm going to get 2i over n quantity squared, which is 4i squared over n squared. So all of this is kind of your setup work as we get ready to start the problem. So as we start, the next thing that we're going to do is we're going to do the limit as n goes to infinity of the sum from I equals 1 to n. My f of x sub I is 4i squared over n squared times delta x, which was 2 over n. Okay? So in this point of the process, n can go out front. Okay? Before we continue, I want to talk about the process. So remember, if I take the limit as x goes to infinity and I have 1 over x. So that function looks like this. As x goes to infinity, then the limit is going to approach 0. So basically what we're doing is we're trying to force this situation to happen when I take the limit, okay? So now I'm going to rewrite my equation. So I'm going to write it as the limit. Remember, anytime we're doing a limit problem, we have to carry the limit notation through until we do the direct substitution. So I'm going to pull the 4 and the 2 out front. That's an 8. And then these n's over n cubed times the sum from I equals 1 to n. And now on the inside, all I have is I squared. Now I'm going to use my summation formulas. So this is the limit as n goes to infinity of 8 over n cubed, and then my I squared is going to be times n plus 1 times 2n plus 1 all over 6, okay? And so then as we progress through these problems, we're going to try to manage this information. I will tell you that these are tedious with algebra, so we're going to be very meticulous. So I'm going to rewrite this as the limit as n goes to infinity. I'm going to move the 6 out with the 8, okay? And then I'm going to cancel, and that's going to leave an n squared. And then I'm going to distribute. So I'm going to get times, and then in the numerator I have 2n squared, right, from here and here, and then plus 2n times 1 is 2n plus n plus 1, and it's all going to be over n squared. So now what I'm going to do is I'm going to split this up into individual terms. So this is the limit as n goes to infinity. 8/6, 2 goes into that, and this is 4 over 3. Okay? Did I do my math right? I think so. So then I'm going to split this up, and I'm going to have 2n squared over n squared plus 2n over n squared plus n over n squared plus 1 over n squared. And so now if we think about taking the limit, the degree in the denominator is higher. This goes to 0. This goes to 0. This goes to 0. This goes to 2. And now I can do, this is 8 over 3, and we're done. So sometimes these problems can be very challenging. So I'm going to write the area was equal to the integral from 0 to 2 of f of x dx was equal to 8/3. Okay, the integration is significantly easier, just like when we started taking derivatives, that was easier. But I'm going to learn this process because it's a necessary evil. All right, so the next example that I want to do, so example number 3, I'm going to do the same problem, except I'm going to do the right-hand limit. So I'm going to have y is equal to x squared. We went from 0 to 2, except this time I'm going to do the right-hand side. Okay, and so I'm going to start the same way I always do. My delta x is going to be b minus a over n, so it's going to be 2 minus 0 over n, so it's 2 over n. My x sub I, except when we're starting on the right, is going to be b minus delta x times I, so it's going to be 2 minus 2 over n times I. My f of x sub I is going to equal this equation, so 2 minus 2 over n times I, quantity squared, okay? I often do the left-hand side, especially when I'm integrating from 0, because in my opinion it's just a lot easier. You can see that for the exact same problem, my f of x sub I is just going to be harder. So now what I'm going to do is I'm going to expand this to make my life a little bit easier. 2 squared is 4. Multiply these two together, and I get 4 over ni times 2, so minus 8i over n. and then square the last term plus 4I squared over n squared. And now I'm going to write my limit as n goes to infinity of the sum from I equals 1 to n of f of x sub I times delta x. So this is the limit as n goes to infinity. My sum I equals 1 to n. Here's my f of x sub I, so I'm going to write 4 minus 8I over n plus 4I squared over n squared times my delta x, which was 2 over n. Okay? So in this particular problem, all I'm going to move is the 2 over n, and then I'm going to continue to work. So then this is the limit as n goes to infinity, and I have 2 over n, and then I have the sum from I equals 1 to n. I'll bring it back in later, but for right now it's just easier. Now I'm going to manage my summation formulas. The summation formula for a constant means that this goes up in power, so it's going to be 4 to the n, okay? And actually this guy goes away because I am actually managing the summation formulas. And then I have minus 8 over n times I, and n times n plus 1 all over 2, okay? There's that term. And then I'm going to manage plus 4 over n squared times I squared, which is n times n plus 1 times 2n plus 1 all over 6. Alrighty, so before I go on, I'm going to try to clean things up a little bit, and I'm not going to distribute this yet. So I have the limit as n goes to infinity. I'm just going to leave the 2 in there. Okay, I have 4 in here. These n's cancel. 2 goes into 8 4 times. So I have minus 4 times n plus 1. Okay. All right, that's the first part. And then this n goes into here, and I'm going to put that in there. And then 2 goes into this 2, 2 goes into this 3. So then I'm going to have plus 2 over 3n times, I'm going to go ahead and expand this piece right here, 2n squared plus n plus 2n plus 1, okay? Alrighty. And if I combine those terms, I'm going to get times 2n squared plus 3n plus 1, okay? All right. So now what I'm going to do, I guess I should close my parentheses, is I'm going to expand this to each one of these individual terms. So I have the limit. I still can't simplify. I'm still just trying to manage all of my terms. So I have 8n over n. There's the first term. Okay. Then I have minus 8 times n plus 1 over n. That's this term right here. Then I have plus 4 over 3n squared times 2n squared plus 3n plus 1. Okay. All right, now I'm going to clean it up a little bit more. So these n's cancel. And then at this point, now I'm going to just separate it out a little bit more as n goes to infinity. So here's the 8. Then I have minus 8n over n minus 8 over n. That's this term right here. And then plus 8n squared over 3n squared plus 12n over 3n squared plus 4 over 3n squared. Whew, that's a lot of math. Okay? And now I'm actually going to take my limit. Those cancel, so therefore those cancel. Alrighty? Those n squareds cancel. This goes to 0. This goes to 0. This goes to 0 because the degree is higher in the denominator. And there's my answer, 8/3. So I got the same answer that I did from the right-hand approximation. That is not common. Oftentimes, one of the approximations is higher, and it is determined by whether or not the function is increasing or decreasing. But for right now, both of them have the same approximation. All right, that was fun. That's it for today, my dear.